Phosphorus is a chemical element with symbol P and atomic number 15. As an element, phosphorus exists in two major forms, white phosphorus and red phosphorus, but because it is highly reactive, phosphorus is never found as a free element on Earth. With few exceptions, minerals containing phosphorus are in the maximally oxidized state as inorganic phosphate rocks. The first form of elemental phosphorus to be produced emits a faint glow when exposed to oxygen, hence the name taken from Greek mythology, Phi Omega Sigma Phi Omicron Rho Omicron Sigma, meaning light bearer, referring to the morning star, the planet Venus. The term phosphorescence, meaning glow after illumination, originally derives from this property of phosphorus, although this word has since been used for a different physical process that produces a glow. The glow of phosphorus itself originates from oxidation of the white phosphorus, a process now termed chemiluminescence. Together with nitrogen, arsenic, and antimony, phosphorus is classified as a pnictogen. Phosphorus is essential for life. Phosphates are a component of DNA, RNA, ATP, and the phospholipids, which form all cell membranes, demonstrating the link between phosphorus and life. Elemental phosphorus was first isolated from human urine, and bone ash was an important early phosphate source. Phosphate minerals are fossils. Low phosphate levels are an important limit to growth in some aquatic systems. The vast majority of phosphorus compounds produced are consumed as fertilizers. Phosphate is needed to replace the phosphorus that plants remove from the soil, and its annual demand is rising nearly twice as fast as the growth of the human population. Other applications include the role of organophosphorus compounds in detergents, pesticides, and nerve agents. At 0.099%, phosphorus is the most abundant pnictogen in the Earth's crust. Characteristics. Physical phosphorus exists as several forms that exhibit strikingly different properties. The two most common allotropes are white phosphorus and red phosphorus. White phosphorus and related molecular forms from the perspective of applications and chemical literature. The most important form of elemental phosphorus is white phosphorus, often abbreviated as WP. It consists of tetrahedral P4 molecules, in which each atom is bound to the other three atoms by a single bond. This P4 tetrahedron is also present in liquid and gaseous phosphorus up to the temperature of 800 degrees Celsius when it starts decomposing to P2 molecules. Solid white exists in two forms. At low temperatures, the beta form is stable. At high temperatures, the alpha form is predominant. These forms differ in terms of the relative orientations of the constituent P4 tetrahedra. White phosphorus is the least stable, the most reactive, the most volatile, the least dense, and the most toxic of the allotropes. White phosphorus gradually changes to red phosphorus. This transformation is accelerated by light and heat, and samples of white phosphorus almost always contain some red phosphorus and accordingly appear yellow. For this reason, white phosphorus that is aged or otherwise impure is also called yellow phosphorus. When exposed to oxygen, white phosphorus glows in the dark with a very faint tinge of green and blue. It is highly flammable and pyrophoric upon contact with air. Owing to its pyrophoricity, white phosphorus is used as an additive in napalm. The odor of combustion of this form has a characteristic garlic smell, and samples are commonly coated with white phosphorus pentoxide, which consists of P4O10 tetrahedra with oxygen inserted between the phosphorus atoms and at the vertices. White phosphorus is insoluble in water but soluble in carbon disulfide. White phosphorus is toxic, causing severe liver damage on ingestion. Thermolysis of P4 at 1100 Kelvin gives diphosphorus P2. This species is not stable as a solid or liquid. The dimeric unit contains a triple bond and is analogous to N2. It can also be generated as a transient intermediate in solution by thermolysis of organophosphorus precursor reagents. At still high temperatures, P2 dissociates into atomic P. Although the term phosphorescence is derived from phosphorus, the reaction that gives phosphorus its glow is properly called chemiluminescence, not phosphorescence. Red phosphorus is polymeric in structure. It can be viewed as a derivative of P4 wherein one pp bond is broken, and one additional bond is formed with the neighboring tetrahedron, resulting in a chain-like structure. Red phosphorus may be formed by heating white phosphorus to 250 degrees Celsius or by exposing white phosphorus to sunlight. Phosphorus after this treatment is amorphous. Upon further heating, this material crystallizes. In this sense, red phosphorus is not an allotrope, but rather an intermediate phase between the white and violet phosphorus, and most of its properties have a range of values. For example, freshly prepared, bright red phosphorus is highly reactive and ignites at about 300 degrees Celsius, though it is more stable than white phosphorus, which ignites at about 30 degrees Celsius. After prolonged heating or storage, the color darkens. The resulting product is more stable and does not spontaneously ignite in air. Violet phosphorus is a form of phosphorus that can be produced by day-long annealing of red phosphorus above 550 degrees Celsius. In 1865, Hittorf discovered that when phosphorus was recrystallized from molten lead, a red-purple form is obtained. Therefore, this form is sometimes known as Hittorf's phosphorus. Black phosphorus is the least reactive allotrope and the thermodynamically stable form below 550 degrees Celsius. It is also known as beta metallic phosphorus and has a structure somewhat resembling that of graphite. Black phosphorus is obtained by heating white phosphorus under high pressures. In appearance, properties, and structure, it resembles graphite, being black and flaky, a conductor of electricity, and has puckered sheets of linked atoms. High pressures are usually required to produce black phosphorus, but it can also be produced at ambient conditions using metal salts as catalysts. Another form, scarlet phosphorus, is obtained by allowing a solution of white phosphorus in carbon disulfide to evaporate in sunlight. Another allotrope is diphosphorus. It contains a phosphorus dimer as a structural unit and is highly reactive. Isotopes. 23 isotopes of phosphorus are known, including all possibilities from 24p up to 46p. Only 31p is stable and is therefore present at 100% abundance. The half-integer nuclear spin and high abundance of 31p make phosphorus 31 NMR spectroscopy a very useful analytical tool in studies of phosphorus-containing samples. 2 radioactive isotopes of phosphorus have half-lives suitable for biological scientific experiments. These are 32p, a beta emitter with a half-life of 14.3 days, which is used routinely in life science laboratories, primarily to produce radio-labeled DNA and RNA probes, e.g., for use in northern blots or southern blots. 33p, a beta emitter with a half-life of 25.4 days. It is used in life science laboratories in applications in which lower energy beta emissions are advantageous, such as DNA sequencing. The high-energy beta particles from 32p penetrate skin and corneas, and any 32p ingested, inhaled, or absorbed is readily incorporated into bone and nucleic acids. For these reasons, Occupational Safety and Health Administration in the United States, and similar institutions in other developed countries, require personnel working with 32p to wear lab coats, disposable gloves, and safe safety glasses or goggles to protect the eyes, and avoid working directly over open containers. Monitoring personal clothing and surface contamination is also required. Shielding requires special consideration. The high energy of the beta particles gives rise to secondary emission of X-rays via bremsstrahlung in dense shielding materials such as lead. Therefore, the radiation must be shielded with low-density materials such as acrylic or other plastic, water, or even wood. Occurrence: minerals. Phosphorus is not found free in nature, but it is widely distributed in many minerals, mainly phosphates. Inorganic phosphate rock, which is partially made of apatite, is today the chief commercial source of this element. According to the U.S. Geological Survey, about 50% of the global phosphorus reserves are in the Arab nations. Large deposits of apatite are located in China, Russia, Morocco, Florida, Idaho, Tennessee, Utah, and elsewhere. Albright and Wilson in the UK and the Niagara Falls plant, for instance, were using phosphate rock in the 1890s and 1900s from Tennessee, Florida, and the Isles du Connet table. By 1950 they were using phosphate rock mainly from Tennessee in North Africa. In the early 1990s, Albright and Wilson's purified wet phosphoric acid business was being adversely affected by phosphate rock sales by China and the entry of the long-standing Moroccan phosphate suppliers into the purified wet phosphoric acid business. In 2012, the USGS estimated 71 billion tons of world reserves, where reserve figures refer to the amount assumed recoverable at current market prices. 0.19 billion tons were mined in 2011. Critical to contemporary agriculture, its annual demand is rising nearly twice as fast as the growth of the human population. Recent reports suggest that production of phosphorus may have peaked, leading to the possibility of global shortages by 2040. In 2007, at the rate of consumption, the supply of phosphorus was estimated to run out in 345 years. However, some scientists now believe that a peak phosphorus will occur in 30 years and that, at current rates, reserves will be depleted in the next 50 to 100 years. Co-founder of Boston-based investment firm and environmental foundation Jeremy Grantham wrote in Nature in November 2012 that consumption of the element must be drastically reduced in the next 20 to 40 years or we will begin to starve. Quote, according to N. Greenwood and A. Earnshaw, authors of the textbook Chemistry of the Elements. However, phosphorus comprises about 0.1% by mass of the average rock, and consequently the Earth's supply is vast, although dilute. Urine contains most of the NPK nutrients excreted by the human body. The more general limitations to using urine as fertilizer depend mainly on the potential for buildup of excess nitrogen, and inorganic salts such as sodium chloride, which are also part of the wastes excreted by the renal system. The degree to which these factors impact the effectiveness depends on the term of use, salinity, tolerance of the plant, soil composition, addition of other fertilizing compounds, and quantity of rainfall or other irrigation. Urine typically contributes 70% of the nitrogen and more than half the phosphorus and potassium found in urban wastewater flows, while making up less than 1% of the overall volume. Thus far, source separation, or urine diversion and on-site treatment, has been implemented in South Africa, China, and Sweden among other countries, with the Bill and Melinda Gates Foundation provided some of the funding implementations. Urine management is a relatively new way to view closing the cycle of agricultural nutrient flows and reducing sewage treatment costs and ecological consequences such as eutrophication distillation resulting from the influx of nutrient-rich effluent into aquatic and marine ecosystems. Proponents of urine as a natural source of agricultural fertilizer claim the risks to be negligible or acceptable. Other organic sources, historically important but limited commercial sources, were organic, such as bone ash and guano. Supernovae remnants. In 2013, astronomers detected phosphorus in Cassiopeia A, which confirmed that this element is produced in supernovae through supernova nucleosynthesis. The phosphorus-to-iron ratio in material from the supernova remnant could be up to 100 times higher than in the Milky Way in general. Production. Most production of phosphorus-bearing material is for agriculture fertilizers. For this purpose, phosphate minerals are converted to phosphoric acid. It follows two distinct chemical routes, the main one being treatment of phosphate minerals with sulfuric acid. The other process utilizes white phosphorus, which may be produced by reaction and distillation from very low-grade phosphate sources. The white phosphorus is then oxidized to phosphoric acid and subsequently neutralized with base to give phosphate salts. Phosphoric acid produced from white phosphorus is relatively pure and is the main route for the production of phosphates for all purposes, including detergent production. Elemental phosphorus. Presently, about 1 million short tons of elemental phosphorus is produced annually. Calcium phosphate, mostly mined in Florida and North Africa, can be heated to 1200 to 1500 degrees Celsius with sand, which is mostly silicon oxide, and coke to produce vaporized P4. The product is subsequently condensed into a white powder underwater to prevent oxidation by air. Even underwater, white phosphorus is slowly converted to the more stable red phosphorus allotrope. The chemical equation for this process when starting with fluoroapatite, a common phosphate mineral, is 4 calcium fluoride plus 18 silicon peroxide plus 30 C3P4 plus 30 CO plus 18 calcium metasilicate plus 2 calcium fluoride. Side products from this process include ferrophosphorus, a crude form of, resulting from air and impurities in the mineral precursors. The silicate slag is a useful construction material. The fluoride is sometimes recovered for use in water fluoridation. More problematic is mud containing significant amounts of white phosphorus. Production of white phosphorus is conducted in large facilities in part because it is energy intensive. The white phosphorus is transported in molten form. Some major accidents have occurred during transportation. Train derailments at Brownston, Nebraska and Miamisburg, Ohio led to large fires. The worst incident in recent times was an environmental contamination in 1968 when the sea was polluted from spillage or inadequately treated sewage from a white phosphorus plant at Placentia Bay, Newfoundland. Another process by which elemental phosphorus is extracted includes applying at high temperatures 2 California 32 plus 6 silicon peroxide plus 10 C6 calcium metasilicate plus 10 CO plus P4. Historically, before the development of mineral-based extractions, white phosphorus was isolated on an industrial scale from bone ash. In this process, the tricalcium phosphate in bone ash is converted to monocalcium phosphate with sulfuric acid. California 32 plus 2 H2SO4 California 2 plus 2 calcium sulfate monocalcium phosphate is then dehydrated to the corresponding metaphosphate. California 2 plus 2 H2O when ignited to a white heat with charcoal. Calcium metaphosphate yields 2/3 of its weight of white phosphorus while 1/3 of the phosphorus remains in the residue as calcium. Orthophosphate 3 California 2 plus 10 C California 32 plus 10 CO plus P4 compounds. Oxoacids of phosphorus. Phosphorus oxoacids are extensive, often commercially important, and sometimes structurally complicated. They all have acidic protons bound to oxygen atoms. Some have non-acidic protons that are bonded directly to phosphorus, and some contain phosphorus bonds. Although many oxoacids of phosphorus are formed, only 9 are important, and 3 of them, hypophosphorus acid, phosphorus acid, and phosphoric acid, are particularly important. Phosphorus compounds. Oxides. The most prevalent compounds of phosphorus are derivatives of phosphate, a tetrahedral anion. Phosphate is the conjugate base of phosphoric acid, which is produced on a massive scale for use in fertilizers. Being triprotic, phosphoric acid converts stepwise to 3 conjugate bases: H3PO4 plus H2OH3O plus H2PO4 minus Ca1 equals 7.25 times 10 minus 3 H2PO4 minus plus H2OH3O plus HPO42 minus Ca2 equals 6.31 times 10 minus 8 HPO42 minus plus H2OH3O plus PO43 minus Ca3 equals 3.98 times 10 minus 13. Phosphate exhibits the tendency to form chains and rings with POP bonds. Many polyphosphates are known, including ATP. Polyphosphates arise by dehydration of hydrogen phosphates such as HPO42- and H2PO4-. For example, the industrially important trisodium triphosphate is produced industrially by the megaton by this condensation reaction. 2Na2 plus NR5 plus 2H2O. Phosphorus pentoxide is the acid anhydride of phosphoric acid, but several intermediates between the two are known. This waxy white solid reacts vigorously with water. With metal cations, phosphate forms a variety of salts. These solids are polymeric, featuring POM linkages. When the metal cation has a charge of 2 plus or 3 plus, the salts are generally insoluble, hence they exist as common minerals. Many phosphate salts are derived from hydrogen phosphate. Phosphorus pentachloride and PF5 are common compounds. PF5 is a colorless gas and the molecules have trigonal bipyramidal geometry. Phosphorus pentachloride is a colorless solid which has an ionic formulation of phosphorus tetrachloride plus phosphorus hexachloride minus, but adopts the trigonal bipyramidal geometry when molten or in the vapor phase. Phosphorus pentabromide is an unstable solid formulated as phosphorus tetrabromide plus Br- and Pi5 is not known. The pentachloride and pentafluoride are Lewis acids. With fluoride, PF5 forms PF6-, an anion that is isoelectronic with SF6. The most important oxyhalide is phosphorus oxychloride, which is approximately tetrahedral. Before extensive computer calculations were feasible, it was thought that bonding in phosphorus compounds involved d orbitals. Computer modeling of molecular orbital theory indicates that this bonding involves only s and p orbitals. Nitrides. The PN molecule is considered unstable, but is a product of crystalline phosphorus nitride decomposition at 1100 K. Similarly, H2PN is considered unstable, and phosphorus nitride halogens like F2PN, Cl2 petanewtons, Br2 petanewtons, and I2PN are ligamerized into cyclic polyphosphazons. For example, compounds of the formula N exist mainly as rings such as the trimer hexachlorophosphazone. The phosphate basins arise by treatment of phosphorus pentachloride with ammonium chloride. Phosphorus pentachloride plus ammonium chloride 1N plus 4 hydrogen chloride when the chloride groups are replaced by alkoxide. A family of polymers is produced with potentially useful properties. Sulfides. Phosphorus forms a wide range of sulfides, where the phosphorus can be in P or other oxidation states. The most famous is the threefold symmetric P4S3, which is used in strike-anywhere matches. P4S10 and P4010 have analogous structures. Phosphorus compounds. All four symmetrical trihalides are well known. Gaseous PF3, the yellowish liquids phosphorus trichloride and phosphorus tribromide, and the solid Pi3. These materials are moisture-sensitive, hydrolyzing to give phosphorus acid. The trichloride, a common reagent, is produced by chlorination of white phosphorus. P4 plus 6Cl2 for phosphorus trichloride. The trifluoride is produced from the trichloride by halide exchange. PF3 is toxic because it binds to hemoglobin. Phosphorus oxide, P4O6, is the anhydride of P3, a minor tautomer of phosphorus acid. The structure of P4O6 is like that of P4010 without the terminal oxide groups. Mixed oxyhalides and oxyhydrides of phosphorus are almost unknown. Organophosphorus compounds. Compounds with PC and POC bonds are often classified as organophosphorus compounds. They are widely used commercially. The phosphorus trichloride serves as a source of P3+ en route to organophosphorus compounds. For example, it is the precursor to triphenylphosphine. Phosphorus trichloride plus 6Na plus 3C6 hydrogen chloride P3 plus 6 sodium chloride. Treatment of phosphorus trihalides with alcohols and phenols gives phosphides, e.g. triphenylphosphite. Phosphorus trichloride plus 3C6H5OH P3 plus 3 hydrogen chloride. Similar reactions occur for phosphorus oxychloride, affording triphenylphosphate. OPCl3 plus 3C6H5OH OP3 plus 3 hydrogen chloride. Phosphorus and phosphorus compounds. These compounds generally feature PP bonds. Examples include catonated derivatives of phosphine and organophosphines. Compounds containing P equals P double bonds have also been observed, although they are rare. Phosphines. Phosphine and its organic derivatives are structural analogues with ammonia, but the bond angles at phosphorus are closer to 90 degrees for phosphine and its organic derivatives. It is an ill-smelling, toxic compound. Phosphorus has an oxidation number of -3 in phosphine. Phosphine is produced by hydrolysis of calcium phosphide. Calcium phosphide. Unlike ammonia, phosphine is oxidized by air. Phosphine is also far less basic than ammonia. Other phosphines are known which contain chains of up to 9 phosphorus atoms and have the formula PNHN+2. The highly flammable gas diphosphine is an analog of hydrazine. Phosphides. Phosphides arise by reaction of metals with red phosphorus. The alkali metals and alkaline earth metals can form ionic compounds containing the phosphide ion, P3-. These compounds react with water to form phosphine. Other phosphides, for example sodium phosphide, are known for these reactive metals. With the transition metals as well as the monophosphides, there are metal-rich phosphides, which are generally hard refractory compounds with a metallic luster, and phosphorus-rich phosphides which are less stable and include semiconductors. Tribosite is a naturally occurring metal-rich phosphide found in meteorites. The structures of the metal-rich and phosphorus-rich phosphides can be structurally complex. Spelling and etymology. The name Phosphorus in ancient Greece was the name for the planet Venus and is derived from the Greek words, which roughly translates as light bringer, a light carrier, Hesperus a Hesperus, and Eosphorus a close homologues, and also associated with Phosphorus the planet. According to the Oxford English Dictionary, the correct spelling of the element is phosphorus. The word phosphorus is the adjectival form of the P3+ valence. So, just as sulfur forms sulfurous in sulfuric compounds, phosphorus forms phosphorus compounds and P5+ valence phosphoric compounds.